The leap from 56 kilobit dial-up to a 10 gigabit fiber optic link is rarely portrayed correctly. We treat it as an achievement in software or processing power. In reality, it represents 4 decades of warfare against the strict physical laws of thermodynamics, moving data from chaotic radio frequencies into flawless optical glass. Every telecommunications medium on Earth operates under a strict mathematical speed limit, defined in 1948 by mathematician Claude Shannon. The Shannon-Hartley theorem proves increasing channel capacity, C, requires manipulating bandwidth, B, and signal-to-noise ratio. Expanding bandwidth invites interference, forcing an artificial boost to signal-to-noise. This mathematical tension dictated the physical compromises of legacy telephony copper and coaxial cable. We are going to examine how architects squeezed maximum capacity out of those aging metal networks, and why physical limits ultimately forced the global transition to optical silica. The speed of global communication is ultimately bound by the specific physics of the materials used in the last mile. The original local copper loop was built strictly for the human voice. At the telephone company's central office, hardware filters deliberately clamped the frequency of every twisted pair down to a mere 4 kilohertz to prevent lines from interfering with each other. Early dial-up modems had to operate entirely inside that narrow, band-limited analog voice channel, squeezing maximum spectral efficiency out of frequencies that were originally meant for human speech. This chart maps the frequency spectrum of early broadband. To move past dial-up, engineers developed digital subscriber line, or DSL. By bypassing the central office voice filters entirely, they could unleash the raw copper, opening up spectrum up to 2.2 megahertz. But pushing high frequencies through unshielded copper triggers the skin effect. Electromagnetic waves face exponentially higher resistance and attenuation at higher frequencies. Over physical distance, the signal-to-noise ratio simply plummets toward zero. To survive this, engineers deployed discrete multitone modulation. This technique chops the available spectrum into tiny independent subchannels, analyzing the line in real time to assign data only to the cleanest frequencies, avoiding the localized noise. Still, as providers pushed frequencies higher to achieve faster speeds, they hit a hard physical wall, far-end crosstalk. The electromagnetic fields from hundreds of adjacent copper lines packed tightly inside street-level binders began leaking into each other. The solution to crosstalk was vectoring, defined by the ITU-T G993.5 standard. By measuring the interference signatures of every line in the binder simultaneously, the network equipment calculates and applies active anti-phase noise cancellation, pre-compensating for the interference before the data even leaves the transmitter. Vectoring and discrete multitone are mathematical illusions. They are sophisticated algorithms designed to artificially boost the signal-to-noise ratio, dragging aging copper networks right up to the limits of the Shannon-Hartley equation. Unlike the point-to-point architecture of telephone wire, community antenna television networks were built as highly shared tree and branch topologies. Pushing data through a coaxial distribution network requires cascading radio frequency amplifiers placed in series along the line. Each amplifier contributes thermal noise to the signal as it travels. This diagram illustrates a critical vulnerability in two-way coaxial networks, the noise funneling effect. Because every home shares the physical medium, ingress noise from poorly shielded cables or home appliances enters the individual branches and aggregates into a massive, concentrated noise spike at the central optical node. This aggregate noise specifically devastates the upstream signal-to-noise ratio, physically starving the network of return capacity. To maintain gigabit speeds over this shared RF medium, the DOCSIS 3.1 standard rewrote the physical layer entirely. Engineers abandoned single-carrier modulation and adopted OFDMA. OFDMA divides wide spectral blocks into thousands of independent subcarriers. Combined with advanced error correction, it allows the cable modem to dynamically route data around polluted frequencies in real time. In clean spectrum blocks, modern DOCSIS networks can push up to 4,096 QAM, achieving downstream speeds of up to 10 gigabits per second, despite operating inside a harsh, noise-filled RF environment. Like copper, the operational lifespan of coaxial cable was extended by deploying highly advanced signal processing to mask the physical degradation of the shared medium. Eventually, the constraints of metallic mediums forced engineers to abandon guided electromagnetic waves in favor of guided light waves trapped inside ultra-pure silica glass. Glass suffers zero electromagnetic crosstalk. Furthermore, its bandwidth operates in the multi-terahertz range, completely bypassing the constraints that crippled radio frequency networks. Network architects operate fiber systems within specific near-infrared spectrums, specifically the 850, 1310, and 1550 nanometer windows, where the silica matrix exhibits its lowest physical attenuation. However, laying a dedicated fiber directly from a central office to every single home is cost-prohibitive. To make fiber to the home economically viable, engineers rely on passive optical networks, which introduce a new physical penalty called insertion loss. This topology diagram displays a passive optical network. Out in the field, unpowered, fused silica waveguides physically divide the incoming light wave into 32 or 64 individual beams that run to subscriber homes. Splitting light degrades its optical power. A standard 1:64 split ratio will inherently destroy roughly 21 decibels of signal power before the light ever reaches a receiver. To expand network capacity without the massive expense of trenching new physical fiber lines, engineers utilize wavelength division multiplexing. Operators can run legacy gigabit connections and modern 10 gigabit symmetrical connections simultaneously on the same physical glass by modulating them at completely separated optical wavelengths, keeping the 1490 nanometer signals completely isolated from the 1577 nanometer signals. Optical fiber defeats the Shannon-Hartley limitations of metallic wire, shifting the engineering challenge entirely away from noise mitigation and into pure optical power budgeting. Because of the strict noise limits on the upstream path, legacy broadband architectures were built to be highly asymmetric, prioritizing massive downstream rates while choking the upstream return. This trade-off made perfect sense for early internet usage. Activities like web browsing and downloading static files efficiently masked the physical limitations of the upstream copper and coax. Modern enterprise architectures shattered that model. Industry 4.0 integrates physical automation with cloud-managed IT environments, heavily relying on continuous telemetry, advanced edge computing, and real-time remote execution. Robotic telesurgery and precision industrial manufacturing require ultra-reliable, low-latency communication. The network must hold latency below the human sensory threshold, with zero packet loss and strictly symmetrical throughput. This diagram contrasts legacy asymmetric traffic flows with modern enterprise requirements. Synchronizing a physical factory floor with a digital twin in a hyperscale cloud environment requires a perfectly symmetrical pipeline. You cannot meet these symmetrical demands by tweaking older radio frequency mediums. Symmetrical throughput requires a complete architectural transition to the optical physical layer. Symmetrical gigabit infrastructure acts as a general-purpose technology, lowering transaction costs and integrating regional markets directly into global supply chains. But deploying this layer is heavily constrained by capital expenditure. Laying physical fiber requires rigorous civil engineering, precise directional boring, and deep trenching. We spent decades writing complex algorithms to force gigabits of data through noisy copper wires and aging coaxial cables. Today, we bury pure silica glass to keep robotic assembly lines perfectly synced with cloud servers. The primary constraint of global telecommunications has moved past the physics of the medium. The modern bottleneck is the spatial economics of digging the trenches to lay the glass.